All right, everyone, welcome back. Ready to dive into some serious wireless communication theory.
Absolutely. Let's get into it.
Today, we're dissecting a chapter straight from an advanced networking textbook.
Overview of wireless communications. It's a good one.
Definitely going to go deeper than your typical intro course.
Yeah.
Think of this as like Wireless Comms 201. You know how we're always talking about designing super efficient systems? Well, all that goes out the window if your data gets lost in the airwaves.
Right. Garbage in, garbage out, as they say, except in this case, it's more like good signal in, garbage signal out.
Exactly. So today we're tackling that challenge head on. How do we make sure our data actually gets where it needs to go, reliably?
It all starts with understanding that the wireless world needs rules, just like any other system.
Okay, so no wireless Wild West then. There's actually a method to the madness.
You bet. We've got regulations and international governing bodies like the ITU, that's the International Telecommunication Union, the FCC here in the US, and the ETSI over in Europe. They're all about keeping things organized, making sure signals don't interfere with each other.
So it's like air traffic control, but for data. I like it.
Yeah.
How does this impact us as computer scientists, though?
Well, it boils down to resource allocation. These organizations determine who gets to use which parts of the radio frequency spectrum.
So we're talking about those limited radio waves that carry our data.
Exactly. Some parts of the spectrum are licensed to specific companies, like the ones providing your mobile phone service.
Okay, that makes sense.
And then you've got unlicensed bands, which are free for anyone to use as long as they follow the rules.
That's where things like Wi-Fi and Bluetooth come into play, right?
Exactly. It's a delicate balance, figuring out how to share this finite resource effectively.
A finite resource. So are we in danger of running out of bandwidth?
It's not quite that dire, but it is a concern. That's why we have these regulations in the first place, to make sure we're using the spectrum efficiently.
So it's like prime digital real estate. Everyone wants a piece of it.
That's a good way to put it. And just like with any limited resource, we need to be smart about how we manage it.
Okay, so we've got limited bandwidth, tons of devices all trying to connect. How do we cram all those signals into the airwaves without them tripping over each other?
That's where things get really interesting. We have something called multiple access schemes, clever ways to allow multiple users to share the same frequency band.
Oh, I've heard of these,
Yeah.
like TDMA and FDMA. Right?
You got it. TDMA is like a well-organized time-sharing system. It divides the frequency band into time slots and assigns each user a specific slot.
So it's like taking turns talking on a walkie-talkie.
Precisely. Then there's FDMA, which divides the frequency spectrum itself into smaller channels, kind of like splitting a highway into multiple lanes.
Okay, so time division and frequency division, those make sense. Are there other ways to do this?
Absolutely. There's also CDMA, code division multiple access. This one's a bit more complex. It allows all users to share the entire frequency band at the same time.
Wait, really? How does that even work? Wouldn't the signals interfere with each other?
That's the beauty of CDMA. It uses special codes to spread each user's signal over the entire bandwidth. The receiver then uses the same codes to separate out the desired signal from the others. It's like everyone's speaking different languages at the same time, but your translator can magically filter out only the conversation you need to hear.
Wow, that's wild. I'm guessing that understanding these different schemes is pretty crucial for us as computer scientists, right?
Absolutely. It's fundamental knowledge for anyone working with wireless networks. Imagine you're designing a new wireless sensor network for an industrial plant. You need to factor in how many devices you'll have, how much data they'll be transmitting, the range requirements. All of that will influence your choice of access scheme.
So choosing the wrong scheme could really mess things up.
You could end up with interference, dropped connections, slow data rates, all sorts of headaches.
Okay, so choosing wisely is definitely key. What about those ISM bands I hear about sometimes?
Ah, yes. ISM stands for Industrial, Scientific, and Medical. These are specific frequency bands set aside for unlicensed use. Think of your Wi-Fi, Bluetooth, even some wireless power transfer technologies.
Ah, so it's like the Wild West of wireless innovation.
In a way, yes. It's a hotbed for innovation because anyone can use these frequencies without jumping through the hoops of licensing. But even in the Wild West, you need to know how to get around right.
Right. So let's talk about how these signals actually travel. What happens when a signal leaves an antenna? What's its journey like?
That's where we get into the fascinating world of signal propagation, which is way more complex than just beaming data in a straight line. We're talking about navigating the real-world buildings, trees, even the weather can affect how a signal travels. It's a bit like we're sending a message in a bottle, hoping it reaches its destination.
But instead of ocean currents, we've got radio waves battling it out with the real world.
Exactly. And that real world can get messy. We can break down signal propagation into three main modes.
Hit me with them.
We've got ground wave, sky wave, and line of sight propagation.
Okay, those sound kind of self-explanatory. Let's start with ground wave. What's the deal there?
Ground wave is how AM radio signals can reach you hundreds of miles away. The radio waves travel along the Earth's surface, following its curvature.
So that's why I can sometimes pick up AM stations from other states. Pretty cool. But AM radio isn't exactly known for its amazing sound quality.
Right. Ground wave propagation is more susceptible to noise and interference, especially at those lower frequencies. It's a trade-off.
Makes sense. What about skywave? That sounds a bit more out there.
Skywave propagation is all about bouncing signals off the ionosphere.
The ionosphere. Okay, you're going to have to refresh my memory on that one.
Right, so the ionosphere is this layer of the Earth's atmosphere way up high, and it's full of charged particles. And depending on the frequency of your radio waves, it can act like a giant mirror, reflecting those signals back down to Earth.
So we're basically using the atmosphere as part of our communication infrastructure.
Exactly, and that's how we get long-distance shortwave radio communication. Think thousands of miles.
Wow, okay. But I'm guessing it's not always reliable, right?
Yeah.
The atmosphere is always changing.
You got it. The ionosphere is definitely a bit finicky. Signal quality can be unpredictable with skywave propagation.
Okay, so we've got ground wave hugging the Earth, skywave bouncing off the atmosphere. What about line of sight? That one sounds the most straightforward.
It is, in a way. Line of sight propagation means the signal travels directly from the transmitter to the receiver, just like a beam of light.
So that's what's happening with our smartphones and Wi-Fi most of the time.
You got it. But even with line of sight, there are challenges. For one thing, signal strength decreases rapidly as the distance increases.
Makes sense, it takes energy to travel.
It's actually even more dramatic than that. Signal strength decreases proportionally to the square of the distance.
Okay, so double the distance and you're getting only a quarter of the signal power. Ouch.
Exactly, and that's just in a perfect world with no obstacles. In reality, our signals have to contend with buildings, trees, all sorts of things.
So it's like an obstacle course for radio waves.
That's a great way to put it. And those obstacles can cause all sorts of funky things to happen to our signals: reflection, diffraction, scattering.
Let's break those down. Starting with reflection, that one seems pretty intuitive.
Right. Reflection is simply when a wave hits a surface and bounces off.
Just like light bouncing off a mirror.
Exactly. But in the case of wireless signals, we're talking about reflections off buildings, walls, even large vehicles.
And those reflections can interfere with the original signal.
Right.
Like echoes in a room.
You got it. That's one of the biggest challenges with multipath propagation.
Multipath propagation.
That's what we call it when a signal takes multiple paths to reach its destination. Those different paths can cause the signal to arrive at the receiver at slightly different times, leading to interference and distortion.
Okay, got it. So that's reflection. What about diffraction? How is that different?
Diffraction is kind of like the signal's ability to bend around obstacles. Imagine a wave hitting the edge of a building. Instead of being completely blocked, some of that wave energy will actually bend around the corner.
So it's like the signal finds a workaround.
Exactly. Diffraction helps explain why you can sometimes still get a signal even if you're not in a direct line of sight with the transmitter. But it's not a perfect solution. The signal will always be weaker when it's had to diffract around something.
Okay, that makes sense. So we've got reflection, diffraction. What was the last one? Scattering?
Right. Scattering is what happens when a signal encounters a bunch of small objects.
Like what? Give me some examples.
Think trees, street signs, even raindrops or fog. All of those can scatter the signal in many different directions.
So it's like the signal's getting bounced around like a pinball.
Kind of. And like those other effects, a little scattering can be a good thing. It can help fill in some gaps in coverage. But too much scattering can make it really hard to extract the original information from the signal.
Okay, so we've got all this bouncing, bending, and scattering going on. It's starting to sound like a real mess. How do engineers actually design reliable wireless systems with all this chaos?
That's where a deep understanding of these propagation mechanisms is essential. We need to know how different frequencies behave in different environments so we can optimize things like antenna placement and signal power.
So it's about working with the environment, not against it. Okay, I can dig that. Now, you mentioned fading earlier. You know, those certain drops in signal strength we sometimes experience. How does that fit into all of this?
Great question. Fading is a major challenge in wireless communication, and it's closely tied to multipath propagation. Essentially, fading is when the signal strength fluctuates rapidly over a short period of time, or distance.
So even if I'm standing still, the signal strength on my phone can go up and down because of all those multiple paths interfering with each other.
Exactly. And to make things even more interesting, we categorize fading into two main types: large-scale fading and small-scale fading.
Okay, so what's the difference?
Large-scale fading is about those big-picture changes in signal strength you experience as you move over longer distances.
So like when I'm driving cross town and my signal bars go up and down.
Exactly. That's largely due to path loss. Remember that inverse square law we talked about? And something called shadowing.
Shadowing, like when something blocks the signal.
Precisely. Large buildings, hills, that kind of thing. Now, small-scale fading, sometimes called Rayleigh fading, is what causes those really rapid fluctuations in signal strength, even when you're barely moving.
Ah, so that's why the music in my headphones cuts out for a second, even when I'm just sitting on the bus. It's infuriating.
That's Rayleigh fading in action, and the faster you're moving, the more rapid those fluctuations become, thanks to something called Doppler spread.
Doppler spread. Okay, this is where my physics knowledge gets a little fuzzy.
Remember the Doppler effect? You know how a siren sounds higher pitched as it approaches you and lower pitched as it moves away?
Oh yeah, like an ambulance passing by.
Exactly. Well, the same principle applies to radio waves. When the transmitter or receiver is in motion, the frequency of the received signal shifts slightly.
Okay, so that makes sense. But how does that tie back to fading?
Well, in a multipath environment, all those different paths will experience slightly different Doppler shifts, which can cause even more rapid and unpredictable fading.
So it's not just about the environment itself, but how things are moving within that environment. That's fascinating. It's like trying to hit a moving target with those signals.
Precisely. Now let's dive into a couple of important concepts that help us quantify these fading effects: coherence time and coherence bandwidth.
Okay, hit me with them.
Think of coherence time as a measure of how long we can assume the channel, meaning the path the signal takes, will remain relatively stable.
So a longer coherence time basically means less fading, right?
Exactly. A longer coherence time makes things more predictable, which is always a good thing in wireless communication. A really short coherence time means the channel is changing rapidly, and that makes it much harder to design robust communication systems.
Okay, I'm starting to see why these concepts matter. What about coherence bandwidth?
Coherence bandwidth is similar to coherence time, but instead of time, it refers to the range of frequencies over which the channel behaves similarly.
Okay, so a wider coherence bandwidth means the channel treats a wider range of frequencies equally. That sounds like a good thing, right?
It can be. If your signal's bandwidth, the range of frequencies it uses, is much smaller than the coherence bandwidth, you have what's called flat fading.
Flat fading.
Basically, the entire signal experiences roughly the same fading effects. It's not ideal, but it's manageable.
Okay, so what's the alternative?
Frequency selective fading. That's when your signal's bandwidth is larger than the coherence bandwidth, and that's when things get tricky.
How so?
Well, in frequency selective fading, different frequency components of your signal will experience different fading effects.
Oh, I see. So some parts of the signal get hit harder than others.
Exactly, and that can really distort the signal at the receiver, making it much harder to decode.
Yikes. So how do you deal with that?
That's where some really clever engineering comes in. There are techniques like equalization and OFDM that help mitigate the effects of frequency selective fading, but that's a topic for another deep dive.
Another day, another deep dive. Okay, this is all starting to click now.
Right.
But we've got one more big player in the wireless world to tackle: noise.
Yes. Noise, the eternal enemy of clear communication.
We touched on different types of noise earlier: thermal noise, intermodulation noise, crosstalk, impulse noise. But how do we quantify all that noise? How do engineers actually measure it?
That's where the concept of noise figure comes in.
Noise figure. Okay, break that one down for me.
Noise figure basically tells us how much a device like an amplifier or a filter degrades the signal-to-noise ratio of a signal.
Okay, so the signal-to-noise ratio, or SNR for short, is how loud the signal is compared to all that background noise. We want a high SNR.
You got it. High SNR means a strong, clear signal, making it easier to extract the information we want.
Makes sense. So how does noise figure fit into all of this?
Well, every device we use in a communication system adds a little bit of its own noise. The noise figure tells us just how much noise each component contributes.
So a low noise figure is what we want, right?
Absolutely. We want devices with noise figures as close to 1 dB as possible.
Why 1 dB?
A noise figure of 1 dB means the device is essentially noiseless, which is the ideal scenario.
Ah, I see. But in the real world, there's always some noise, right?
Always. It's like trying to eliminate all the friction in a machine. You can minimize it, but you can never truly get rid of it completely.
So it sounds like engineers are always trying to find that sweet spot, balancing the need to boost the signal with the need to keep noise levels in check.
Exactly. And that brings us back to a concept we touched on earlier, the Ebene-Narita ratio.
Right. The energy per bit to noise power density ratio. It's one of those fundamental concepts that always seems to come up. Why is it so important?
The Ebene-Narita ratio is all about understanding the limits of reliable communication. It tells us how much signal power we need to achieve a certain level of reliability given a certain noise level. So the higher the Ebene, the better.
Because a higher Ebene means a lower bit error rate, and fewer errors mean our data is more reliable.
Exactly. So if you're designing a system for a really noisy environment, like, say, an industrial plant with lots of machinery and interference, you'd aim for a higher Ebene.
That makes a lot of sense. You might need a stronger signal, more sophisticated error correction techniques, or even a completely different way of transmitting the data.
You got it. It's all about understanding the trade-offs and optimizing the system for the specific environment it'll be operating in.
This is really all starting to come together. It's amazing how all these different concepts we've talked about, from propagation to fading to noise, all play a role in making wireless communication possible.
It's a testament to the ingenuity of engineers who've managed to create these systems that work so reliably despite all the challenges.
It really is incredible when you think about it. Well, I think we've covered a ton of ground today. From those invisible radio waves to the very real challenges of noise, fading, and interference, it's been quite a journey.
And the journey's not over. As we keep pushing the boundaries of wireless communication, faster speeds, greater reliability, more devices, new applications, there will always be new challenges to solve and new innovations to explore.
That's what makes this field so exciting. There's always something new to learn and discover. Well, thanks for joining us for this deep dive into the amazing world of wireless communication. Until next time, keep those signals strong and those bit error rates low.